Here is something you have almost certainly done without thinking about it. You looked at a clock today. Maybe it was your phone. Maybe it was a watch on your wrist. Maybe it was the microwave in your kitchen, silently judging you for reheating leftovers at midnight. You glanced at it, read a number, and moved on. You did not panic. You did not question the nature of reality. You did not suddenly wonder whether the number on that clock meant the same thing in every corner of the universe. And that is perfectly reasonable. That is also about to become a problem. Because the number on your clock, that quiet, obedient little number, is lying to you, not maliciously, not dramatically, but in a way so deep, so fundamental, that it took the greatest physicist in a century to even begin to untangle it. And the truth he found is this: the time on your clock is not the same as the time on every other clock in the universe. It never was. It never can be. Right now, as you sit here, there are clocks ticking at slightly different rates depending on how high they are above the ground. The clock on your wrist is ticking at a very slightly different rate than a clock on a satellite orbiting overhead. A clock on the floor of your room is ticking very slightly slower than a clock on your ceiling. These differences are tiny, so small that no human sense could ever detect them. But they are real. They are measured. And if they were ignored, your phone's map would be wrong by kilometers within a single day. But it gets stranger. If you could somehow travel at nearly the speed of light, fast enough to cross the galaxy and come back, you would return to find that everyone you left behind had aged decades, while you had aged only months. Your friends would be old, the world would be different, and you would still be young, carrying the proof of relativity written into your own body. This is not science fiction. This is not speculation. This is what the equations of physics demand, and every experiment ever conducted confirms it. So what is time? Is it a river flowing through the universe? Is it a dimension like space? Is it something that exists independently of everything else, ticking away in the background of reality? Or is it something far stranger, something that bends, stretches, slows, and perhaps even emerges from a deeper reality that has no time at all? That is what we are going to figure out, not by guessing, not by feeling, but by following the evidence, the mathematics, and the experiments that have forced physics to completely reinvent its understanding of what time actually is. We are going to start at the very beginning, with a shadow moving across stone, and follow the story all the way to the edge of human knowledge, where the question of time becomes the deepest unsolved problem in all of physics. Let us begin. Before we can understand what time is, we need to understand something more basic. What is a clock? This sounds like a trivial question. A clock is a thing that tells time. Duh. But that answer is circular. It says a clock measures time, and time is what clocks measure. That is like saying a ruler measures length, and length is what rulers measure. It is technically true, but completely unhelpful. Physics needs something better, and the answer physics gives is surprisingly elegant. A clock is any physical system that repeats a process in a regular way. That is it. That is the whole idea. A clock does not need to understand time. It does not need to sense some mysterious cosmic flow. It just needs to do the same thing over and over, at intervals that are as equal as possible. A pendulum swings back and forth. That is a clock. A quartz crystal vibrates at a steady frequency when electricity passes through it. That is a clock. The Earth rotates on its axis. That is a clock. The moon orbits the Earth. That is a clock. An atom transitions between two energy states and emits radiation at a precise frequency. That is the best clock we have ever built. The history of timekeeping is really the history of finding better repeating processes. The earliest humans read time from the sky. The sun rose and set. That gave them the day. The moon changed shape in a regular cycle. That gave them the month. The seasons shifted in a long pattern. That gave them the year. These were astronomical clocks, written across the heavens in slow motion. But the sky is not always visible. Clouds roll in, night falls. And so humans began building their own clocks. The Egyptians created obelisks that cast shadows, essentially the first sundials, around 3,500 years ago. Water clocks appeared in Babylon and Egypt, using the steady drip of water from one container to another. The Chinese developed incense clocks, where different scents marked different times of day, which is honestly a more pleasant alarm than what most of us deal with. In medieval Europe, mechanical clocks emerged. The earliest ones used a verge escapement, a mechanism that allowed a weight to fall in controlled steps, turning gears at a steady rate. These clocks were not accurate by modern standards. They could be off by 15 minutes or more per day. But they represented something revolutionary. The idea that time could be mechanized, separated from the sky, and placed inside a human-made device. Then came Galileo. The story, possibly apocryphal but too good to ignore, is that a young Galileo watched a chandelier swinging in the Cathedral of Pisa. He timed it against his own pulse and noticed something remarkable. Whether the chandelier swung in a wide arc or a narrow one, each swing took roughly the same amount of time. The period of a pendulum depends on its length, not on how far it swings. This insight would eventually lead to the pendulum clock. Christian Huygens built the first working pendulum clock in 1656. It was accurate to about 15 seconds per day, a massive improvement over earlier mechanical clocks. Huygens spent years refining the design, trying to make the pendulum's path follow a perfect curve called a cycloid, which would make the swing truly isochronous, the same period regardless of amplitude. The quest for accuracy continued. John Harrison, a self-taught English carpenter and clockmaker, spent decades building marine chronometers that could keep accurate time at sea. The problem was the longitude problem. If you wanted to know your east-west position on the ocean, you needed to know the exact time at a reference point and compare it with local noon. Harrison's fourth marine chronometer, the H4, completed in 1761, was accurate to within a few seconds over a transatlantic voyage. It solved one of the greatest practical problems of the age of exploration. And then came the atomic age. In 1955, Louis Essen and Jack Perry at the National Physical Laboratory in England built the first practical atomic clock using cesium atoms. The principle is breathtaking in its simplicity. An atom of cesium-133 has a natural resonance, a specific frequency of microwave radiation that causes it to transition between two energy levels. That frequency is 9,192,631,770 cycles per second. It is the same for every cesium-133 atom, everywhere in the universe, as far as we can tell. Since 1967, the second has been officially defined as exactly 9,192,631,770 oscillations of the radiation corresponding to the transition between two hyperfine energy levels of the cesium-133 atom. That is not a poetic definition. That is the actual, official, international definition. When your phone tells you the time, it is ultimately tracing back to this atomic standard. Modern optical atomic clocks go even further. They use atoms like strontium or ytterbium, which oscillate at much higher frequencies, hundreds of trillions of cycles per second. The best of these clocks are so precise that they would not lose or gain a single second in 30 billion years. That is more than twice the current age of the universe. Let that sink in for a moment. We have built a clock so accurate that it could tick perfectly from the Big Bang to the present day and beyond, and it would still be keeping perfect time long after every star in the universe has burned out. But here is the strange part. Even these perfect clocks do not all agree with each other. A clock on the ground floor of a building ticks at a very slightly different rate than a clock on the top floor. A clock on a fast-moving airplane ticks at a very slightly different rate than a clock on the ground. These differences are not failures of engineering. They are features of reality. To understand why, we need to go back to a time when everyone believed time was simple. Isaac Newton gave physics one of its most powerful ideas. It was not a gadget. It was not an equation. It was a philosophical commitment so deep that it shaped the next 2 centuries of science. Newton believed in absolute time. In his great work, The Principia, published in 1687, Newton wrote, "Absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external." Read that again. Without relation to anything external. Newton was saying that time flows on its own, steady and unchanged, regardless of what is happening in the universe. Whether you are sitting still or flying through space, whether you are at the bottom of a mountain or the top, whether you are in a strong gravitational field or floating in empty void, time passes the same for you. The same seconds tick for everyone, everywhere, always. This was not a casual statement. It was the foundation of Newtonian mechanics, and it was spectacularly successful. Think about what this idea makes possible. If time is absolute, if every observer shares the same clock, then you can write down equations of motion that work for everyone. Position tells you where something is. Velocity tells you how its position changes with time. Acceleration tells you how its velocity changes with time. Force tells you what causes that acceleration. The whole system clicks together like a precision machine. And time is the universal metronome ticking in the background. Newton did not invent this idea from nothing. Galileo had already laid the groundwork. In the early 1600s, Galileo studied falling bodies, rolling balls, and pendulums with extraordinary care. He showed that a ball rolling down an inclined plane accelerates uniformly, that its speed increases in a predictable way with time. He showed that the distance it travels is proportional to the square of the time elapsed. Time was becoming a measurable mathematical quantity. Newton took Galileo's insights and built a complete system. His 3 laws of motion, combined with his law of universal gravitation, could describe an apple falling from a tree and the moon orbiting the Earth. The same mathematics that explained a ball rolling across a table also explained the tides, the paths of comets, and the orbits of planets. This was the great unification. The idea that the heavens and the earth obey the same laws. And it all worked because of absolute time. Every observer could write down the same equations. They might disagree about velocities. A person on a ship sees a dropped ball fall straight down, while a person on shore sees it follow a curved path. But they agreed on the time elapsed. The seconds were the same for everyone. For everyday life, this picture is still beautiful and effective. If you throw a ball, build a bridge, design a machine, or steer a ship, Newtonian physics gives you answers so accurate that the deeper theories are unnecessary. Engineers use Newton every day. The GPS in your phone uses Newton's mechanics as a starting point. The rockets that launch satellites into orbit were designed using Newton's equations. Newton's time was not wrong. It was incomplete. The problem was hiding in something that seemed completely unrelated: light. By the middle of the 19th century, physics had two magnificent achievements. On one side stood Newton's mechanics, the science of motion, forces, and gravity. On the other side stood a new and rapidly growing understanding of electricity and magnetism. The two did not obviously connect. Newton described how objects move. Electricity and magnetism described invisible forces that could make sparks jump, needles spin, and currents flow through wires. They seemed like different branches of knowledge. Then James Clerk Maxwell changed everything. Maxwell was a Scottish physicist who took the experimental work of Michael Faraday and turned it into mathematics. Faraday had discovered that electric and magnetic fields could interact. A changing magnetic field could create an electric current, and vice versa. He imagined these fields spreading through space, curving around charges and wires, filling the space between objects with invisible lines of force. Maxwell expressed Faraday's physical intuition in a set of equations. These four equations, now known as Maxwell's equations, described how electric and magnetic fields create and sustain each other. They unified electricity and magnetism into a single theory, electromagnetism. And then, Maxwell calculated something that shook the foundations of physics. His equations predicted that a changing electric field creates a changing magnetic field, which in turn creates a changing electric field, and so on, an electromagnetic wave propagating through space. When Maxwell calculated the speed of this wave, he got a number, approximately 300,000 kilometers per second. That was the known speed of light. Maxwell had not set out to explain light. He had set out to understand electricity and magnetism. But his equations revealed that light is an electromagnetic wave. Ripples of electric and magnetic fields traveling through space at a speed determined by the fundamental properties of electromagnetism itself. This was magnificent, but it carried a quiet difficulty. In Newton's world, speeds add together. If you are walking forward on a moving train, someone on the platform adds your walking speed to the train's speed. If a carriage is moving and someone throws a ball from it, an observer on the ground measures the ball's speed as a combination of both. This is ordinary, intuitive, and deeply unsurprising. But Maxwell's equations gave light a specific speed, not relative to any particular object, but built into the structure of electromagnetism itself. The speed of light in a vacuum was approximately 300,000 kilometers per second, period. Not 300,000 kilometers per second relative to the lamp that emitted it. Not 300,000 kilometers per second relative to the person measuring it. Just 300,000 kilometers per second. This raised an uncomfortable question. 300,000 kilometers per second? Relative to what? At the time, most physicists had a ready answer. They proposed that light waves, like sound waves and water waves, must travel through a medium. Sound travels through air. Water waves travel through water. Vibrations in a rope travel through the rope. So light, they reasoned, must travel through some medium filling all of space. They called this hypothetical medium the luminiferous ether. The ether was a bold idea with a demanding job description. It had to be stiff enough to carry extremely fast light waves. It had to be thin enough not to slow down the planets as they orbited the sun. It had to be present everywhere, filling all of space, and yet completely undetectable by any direct means. If the ether existed, then the Earth must be moving through it as our planet orbited the sun. That motion should create an ether wind, a bit like the apparent wind you feel when cycling through still air. And that ether wind should affect the measured speed of light. Light moving with the wind should travel at a slightly different speed than light moving against it. The stage was set for one of the most important experiments in the history of physics. In 1887, two American physicists, Albert Michelson and Edward Morley, set out to detect the ether wind. Michelson was a master of precision measurement. He had developed an instrument called an interferometer, which could split a beam of light into two paths, send the beams in perpendicular directions, and then recombine them. When the beams came back together, they created an interference pattern, a series of light and dark bands that depended on the exact distances traveled by each beam. The idea was elegant. If the Earth was moving through the ether, one beam would travel parallel to the motion and the other perpendicular. The beam traveling parallel should be slightly affected by the ether wind. Its travel time would be different, depending on whether it was going with or against the wind. When the two beams were recombined, the interference pattern should shift. Michelson and Morley set up their experiment in a basement laboratory in Cleveland, Ohio. They placed their interferometer on a massive stone slab to reduce vibrations. They floated the slab on mercury so it could be rotated smoothly. They made their measurements with extraordinary care. They expected to find a shift. They found nothing. The interference pattern did not change when the apparatus was rotated. There was no detectable difference in the speed of light in different directions. The ether wind, if it existed, was undetectable. This was not a small problem. It was a crisis. The experiment was repeated many times over the following years, with increasing precision. The result was always the same. No ether wind, no change in the speed of light based on the motion of the observer. Several brilliant physicists tried to explain the result within the existing framework. Hendrik Lorentz and George Fitzgerald independently suggested that objects moving through the ether might contract slightly in the direction of motion, just enough to exactly cancel out the expected effect. This was the Lorentz-Fitzgerald contraction, and it was a mathematical fix that made the numbers work. But it was a patch, not an explanation. Why would objects contract in just that way? What physical mechanism could cause it? The answer would come from a young patent clerk in Bern, Switzerland, who was about to rethink everything. In 1905, Albert Einstein published a paper titled On the Electrodynamics of Moving Bodies. It was one of the most revolutionary papers in the history of science. And it began with something deceptively simple. Two principles. The first principle was not new. It was the principle of relativity, the idea that the laws of physics are the same for all observers moving at constant speed in a straight line. This was already accepted in Newtonian mechanics. If you are on a smoothly moving train and you drop a ball, it falls straight down, just as it would on the ground. The laws of physics do not care whether you are sitting still or moving at a constant velocity. There is no experiment you can do inside a closed room to determine whether you are moving or standing still, as long as your motion is steady and straight. An observer in this kind of steady, non-accelerating motion is said to be in an inertial reference frame. A train moving at constant speed, a spacecraft drifting through empty space, a person standing still on a platform. All of these can be treated as inertial frames, as long as we ignore the small effects of Earth's rotation and gravity for the moment. The second principle was the revolutionary one. Einstein stated, "The speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the light source or the observer." This sounds innocent enough, but its consequences are staggering. Think about what this means. If you are standing still and you measure the speed of a light beam, you get 300,000 kilometers per second. Now imagine you are on a spaceship traveling at 200,000 kilometers per second, and you measure the speed of the same light beam. You would expect, based on everyday intuition, that the light would appear to be moving at only 100,000 kilometers per second relative to you. The speed of light minus the speed of your ship. But that is not what happens. You still measure the speed of light as 300,000 kilometers per second. Not approximately. Not after some adjustment. Exactly the same. This is completely unlike anything in everyday experience. If a car is driving towards you at 100 kilometers per hour, and you are driving toward it at 100 kilometers per hour, the two cars approach each other at 200 kilometers per hour. Speeds add. But light does not play by those rules. For the speed of light to be the same for all observers, something else must give. And what gives is our naive ideas about space and time. Einstein realized that if the speed of light is constant, then measurements of distance and duration must depend on the motion of the observer. Two observers moving relative to each other can measure different distances between the same 2 points. They can measure different times between the same two events. They can even disagree about whether two events happening at different locations occur at the same time or not. That last point, the relativity of simultaneity, is one of the deepest ideas in all of physics, and it is worth understanding carefully. Imagine a long train moving smoothly past a station platform. A person stands at the exact center of the train. Another person stands at the exact center of the platform. Now imagine that two bolts of lightning strike the front and back of the train simultaneously, or at least simultaneous from the point of view of the person on the platform. The lightning leaves marks on both the train and the platform. The person on the platform sees light from both strikes arrive at the same moment. Since they are standing exactly halfway between the two marks on the platform, they conclude the two strikes happened at the same time. But the person on the train is in a different situation. As the light from the two strikes travels toward them, the train is moving. The person on the train is moving toward the light coming from the front of the train and away from the light coming from the back. Since the speed of light is the same in all directions for that person, that is Einstein's second postulate, the light from the front strike arrives first. The person on the train therefore concludes the front strike happened before the back strike. Both observers are correct. Both are using the same laws of physics. Both are measuring light at the same speed. Neither one is confused. They simply disagree about simultaneity. This is not a trick of perception. It is not because the person on the train did not account for the motion of the train. It is a fundamental feature of how space and time work. And once simultaneity becomes relative, another consequence follows naturally. Moving clocks run slow. Here is how to see it. Imagine a very simple clock, two mirrors facing each other, with a pulse of light bouncing back and forth between them. Each bounce is one tick. If the clock is sitting still next to you, the light travels straight up and down. The path is short. The ticks are regular. Now imagine that clock is on a spaceship flying past you at high speed. From the point of view of someone on the spaceship, the light still bounces straight up and down. Nothing unusual. Their clock is working perfectly normally. But from your point of view, watching the spaceship fly past, the light does not travel only up and down. While the light is moving between the mirrors, the whole spaceship is moving sideways. So the light follows a longer diagonal path. It has farther to travel between ticks. Here is the critical point. The speed of light is the same for both of you. The light cannot speed up to cover the longer path in the same amount of time. So from your perspective, each tick of the moving clock takes longer. The moving clock is running slow. This is time dilation. It is not an illusion. It is not a delay caused by light reaching your eyes. It is a real difference in elapsed time measured by physical clocks. The traveler on the spaceship does not feel anything strange. Their clock, their heart, their breathing, their chemistry, everything in their frame of reference is normal. Time dilation only appears when different observers, moving relative to each other. Compare their measurements. The size of the effect is described by a quantity called the Lorentz factor. At everyday speeds, walking, driving, even flying in a jet, the Lorentz factor is so close to 1 that the effects of time dilation are immeasurably small. But as speed approaches the speed of light, the Lorentz factor grows rapidly. Time dilation becomes dramatic. This is not just a theoretical prediction. Nature actually does it. Muons are unstable particles created when cosmic rays from space strike atoms high in Earth's atmosphere. A muon at rest exists for only about 2.2 millionths of a second before it decays. Even traveling near the speed of light, a muon should not survive long enough to reach the ground. But many muons do reach the ground. Detectors on mountaintops and at ground level measure them in large numbers. The explanation is time dilation. From Earth's frame of reference, the fast-moving muons experience time more slowly. Their internal clocks, their decay processes, run slow compared with clocks on Earth, so they travel much farther through the atmosphere than they otherwise could. In 1971, physicists Joseph Hafele and Richard Keating flew highly accurate atomic clocks on commercial aircraft around the world. Some flew eastward, some westward, and some stayed on the ground. When the flying clocks were compared with the ground clocks, they showed small but measurable differences in elapsed time, exactly matching the predictions of relativity. Time dilation is real. Moving clocks genuinely accumulate less time along their paths than clocks that remain at rest. And this leads to one of the most famous thought experiments in all of physics. Imagine two twins. One stays on Earth. The other boards a spaceship, accelerates to near the speed of light, travels to a distant star, turns around, and comes back. When the twins reunite, something extraordinary has happened. The twin who traveled through space has aged less than the twin who stayed home. The traveler might have experienced only a few years, while decades have passed on Earth. At first, this sounds like a contradiction. Special relativity says motion is relative. From the traveler's point of view, Earth was the thing moving away. So why should one twin be younger? The answer is that the two twins did not experience the same kind of journey. The twin who stayed on Earth remained in approximately the same inertial reference frame the entire time. The traveling twin, however, had to accelerate to leave Earth, to turn around, and to return. Acceleration changes your reference frame. The two journeys through spacetime are not symmetrical. This brings us to one of the most important concepts in relativity: proper time. Proper time is the time measured by a clock traveling along its own path through spacetime. Your wristwatch, your heartbeat, your chemical reactions, they all follow your proper time. You never feel your own time slowing down. Locally, your seconds feel like seconds. Your tea cools normally. Your thoughts proceed at their usual pace. But different paths through spacetime contain different amounts of proper time. Think of it like walking through a landscape. Two people can start at the same cottage and end at the same hilltop. One takes a direct path. The other wanders through a valley, around a lake, up a ridge, and back down. They share the same start and finish, but they have walked different distances. In relativity, something similar happens with time. Two observers can begin together, separate, and reunite. Their clocks then reveal how much proper time each path contained. The traveling twins' path through spacetime contains less proper time than the stay-at-home twins' path. The traveling twin is not merely seen as younger. They really have aged less. Fewer heartbeats have occurred. Fewer chemical changes have accumulated. Less biological aging has taken place. When they stand together again, the difference is real and physical. In 1908, Hermann Minkowski, who had been one of Einstein's mathematics teachers, gave special relativity a beautiful geometric interpretation. He argued that space and time should not be treated as separate things. They form a single four-dimensional structure, spacetime. An event in physics is something that happens at a particular place and a particular time. A flash of lightning, a heartbeat, a clock ticking. Each event has a location in space and a moment in time. Minkowski showed that these are not independent. Different observers can slice space-time into space and time differently. But the underlying structure, the space-time interval between events, remains the same for everyone. This was the geometric foundation of special relativity. Time was no longer a separate river flowing behind events. It was woven into the fabric of reality itself. But Einstein was not finished. Special relativity dealt with observers moving at constant speed. No acceleration, no gravity. The next question was inevitable. What happens when gravity enters the story? In Newton's picture, gravity was a force acting across space. The Earth pulled on the moon. The sun pulled on the Earth. Time flowed independently in the background, while gravity moved objects through space. Einstein changed this picture completely. In 1915, he completed the general theory of relativity, and it did something extraordinary. General relativity does not describe gravity as a force pulling objects across a fixed stage. It describes gravity as the curvature of space-time itself, caused by mass and energy. Matter and energy shape space-time. The shape of space-time guides the motion of matter and energy. A planet orbiting the sun is not being tugged by an invisible rope. It is following the straightest possible path through curved space-time. A falling apple is not being pulled in the old Newtonian sense. It is moving along the natural path available to it in space-time geometry shaped by the Earth. And because space-time includes time, gravity does not only affect motion through space. Gravity affects the rate at which time passes. A clock deeper in a gravitational field ticks more slowly than a clock farther away. A clock at sea level ticks very slightly more slowly than a clock on a mountain. A clock in orbit, farther from Earth's center, in a weaker part of Earth's gravitational field, ticks faster than a clock on the ground. The first direct test of this came in 1959. Robert Pound and Glenn Rebka at Harvard University measured the gravitational redshift of gamma rays traveling up and down a 22.5-meter tower in the Jefferson Physical Laboratory. Light climbing away from Earth loses a tiny amount of energy and its frequency shifts downward. Light falling toward Earth gains energy and shifts upward. The experiment confirmed the prediction. Earth's gravity, over a height of just 22.5 meters, was enough to produce a measurable effect. Not a mountain, not a black hole, just a tower in Massachusetts. Since then, gravitational time dilation has been tested with far greater precision. Modern optical atomic clocks are so sensitive that even height differences on the scale of centimeters can be detected through changes in clock rate. The ceiling of your room is aging very slightly faster than the floor. Not by much, not enough to matter for any practical purpose, but enough that the principle is real and measured. This is important because gravitational time dilation is not just an exotic effect near black holes. It exists around every mass, every star, every planet, every building, every person. Every object with mass curves space-time, and every curved space-time affects the passage of time. Near a neutron star, the effect is far stronger. Near a black hole, it becomes one of the defining features of the environment. But the principle is universal. Gravity and time are linked because gravity is the shape of space-time, and clocks measure paths through space-time. And this has a direct, practical consequence that affects your daily life. When you open a map application on your phone, a small blue dot shows you where you are. That dot depends on signals from satellites high above Earth, part of the Global Positioning System, or GPS. The basic idea is straightforward. A satellite broadcasts a radio signal that says where it is and when the signal was sent. Your phone's receiver picks up that signal and compares the sending time with the receiving time. Since radio signals travel at the speed of light, the tiny time delay tells your phone how far away the satellite is. By combining signals from multiple satellites, your phone calculates your position. This works beautifully, but only if the clocks are accurate. And this is where relativity enters. GPS satellites orbit about 20,200 kilometers above Earth's surface. They carry extremely precise atomic clocks. But those clocks do not tick at exactly the same rate as clocks on the ground, for two reasons. First, the satellites are moving fast as they orbit, about 14,000 kilometers per hour. Because of special relativity, this motion causes the satellite clocks to tick very slightly slower than ground clocks. From the ground's perspective, the moving clocks lose about 7 microseconds per day. Second, the satellites are much higher up in a weaker part of Earth's gravitational field. Because of general relativity, this causes the satellite clocks to tick very slightly faster than ground clocks. The gravitational effect is about 45 microseconds per day. The two effects push in opposite directions. The net result is that satellite clocks tick faster than ground clocks by about 38 microseconds per day. 38 millionths of a second. It sounds trivial, but light travels about 11 kilometers in 38 microseconds. If the relativistic correction were ignored, GPS position estimates would drift by about 11 kilometers per day. Within a week, the system would be useless. Within a month, it would be telling you that you are in a completely different city. Every time you use GPS, every time you navigate with your phone, track a delivery, or find a nearby restaurant, you are relying on Einstein's theory of relativity. The quiet little blue dot on your map is a direct, practical consequence of the fact that time runs differently at different heights and at different speeds. This is not a metaphor. It is not a thought experiment. It is an engineering reality built into the firmware of every GPS receiver on the planet. Relativity is not just an elegant theory tucked away in a physics textbook. It is part of the machinery of modern civilization. Financial markets use accurate timing to order transactions. Telecommunications networks rely on synchronized clocks. Power grids, data centers, and scientific observatories all depend on precise timekeeping. Timekeeping so precise that the effects of relativity can no longer be ignored. Near a black hole, time becomes dramatically strange. Black holes are not magical holes in space or cosmic drain plugs. They are extreme predictions of general relativity, places where so much mass is compressed into such a small region that space-time becomes intensely curved. The first exact black hole solution was found by Carl Schwarzschild in 1916, just months after Einstein completed general relativity. Schwarzschild was serving on the Eastern Front in World War I when he worked out the mathematics. He found that if enough mass is compressed within a certain boundary, there is a region from which nothing, not even light, can escape. That boundary is called the event horizon. The event horizon is not a solid surface. It is not a wall or a shell waiting in space. It is a boundary in space-time. Once something crosses it inward, all possible future paths lead deeper in. Escaping would require traveling faster than light, and relativity does not allow that. Time near the event horizon is especially strange when viewed from far away. Imagine a clock falling toward a black hole. To someone watching from a safe distance, the falling clock appears to slow down as it approaches the horizon. Its signals become stretched out. Its light becomes more and more redshifted, losing energy as it climbs away from the black hole's gravity. In the mathematical ideal, the clock seems to freeze at the horizon, ticking more and more slowly, never quite reaching the last tick. But that is not what the falling clock experiences. For an observer falling with the clock, local time feels normal. Their heart beats normally. Their watch ticks normally. If the black hole is large enough that tidal forces at the horizon are not immediately destructive, they could cross the event horizon without feeling a sudden bump. There is no sign saying, "You are now entering a very poor life decision." This is an important distinction. The distant observer sees the clock freeze. The falling observer crosses the horizon in a finite amount of their own proper time. Time does not stop for the person falling in. That description belongs to the distant observer's increasingly delayed view. Real astrophysical black holes also rotate, because they form from spinning stars and grow by swallowing material with angular momentum. In 1963, Roy Kerr found the solution to Einstein's equations describing a rotating black hole. A rotating black hole does not merely curve spacetime. It drags spacetime around with it, an effect called frame dragging. The region outside the event horizon where this dragging becomes unavoidable is called the ergosphere. For a long time, black holes were treated by some scientists as mathematical curiosities rather than real objects. That has changed dramatically. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from two black holes merging about 1.3 billion light-years away. These ripples in spacetime, predicted by Einstein exactly a century earlier, confirmed that black holes are real astrophysical objects that collide, merge, and send waves through the fabric of reality. In 2019, the Event Horizon Telescope produced the first direct image of a black hole's shadow, the supermassive black hole at the center of the galaxy, Messier 87. In 2022, it imaged the black hole at the center of our own Milky Way, Sagittarius A. These images show the dark silhouette of the event horizon against the glow of superheated matter falling in. Black holes reveal time at its most extreme. They show that time can stretch, slow, and differ radically between observers depending on gravity and motion. They make clear that time is not a universal background, flowing evenly through all places. It is woven into spacetime, and spacetime can be bent into extraordinary shapes. Time does not merely pass. It seems to point. Ice melts into water, but a puddle does not gather itself back into a neat ice cube. Coffee cools on a table, but a lukewarm cup does not suddenly steal warmth from the room and become hot again. Wood burns into ash, but ash does not casually reassemble itself into a log. A broken cup stays broken. This one-way direction is called the arrow of time, and it is one of the deepest puzzles in all of physics. The arrow of time is not about clocks ticking. A clock can count seconds in either direction. The arrow is about the physical difference between past and future. The reason some processes seem natural in one direction and absurd in the other. The key to understanding this arrow is entropy. Entropy is often described as disorder, and that is a useful first approximation. But in physics, it is more precise than that. Entropy is connected to the number of microscopic arrangements that can produce the same large-scale state. Imagine a deck of cards arranged perfectly by suit and number. There are very few arrangements that count as that exact ordered deck. Now imagine the same deck shuffled randomly. There are enormously many ways for the cards to be mixed. If you shuffle again and again, the deck is overwhelmingly more likely to move from order into disorder than to accidentally return to perfect order. The same principle applies to physical systems. Gas molecules released in one corner of a room spread out because there are vastly more microscopic ways for them to be spread throughout the room than gathered in one corner. Heat spreads because energy has many more ways to distribute itself among particles than to remain concentrated in one place. This tendency is expressed in the second law of thermodynamics. In an isolated system, entropy tends to increase. The word tends is important. The second law is statistical. It is not saying that every individual particle is commanded to become messier. It is saying that for systems made of enormous numbers of particles, high entropy states are overwhelmingly more likely than low entropy states. The science of entropy was built by several major figures. Rudolf Clausius developed the concept in thermodynamics and gave entropy its name. Ludwig Boltzmann connected it to the microscopic behavior of atoms. Josiah Willard Gibbs developed powerful mathematical tools for understanding statistical ensembles. But the arrow of time leads to a deeper question. If entropy tends to increase, why was entropy low enough in the past for it to increase from there? The early universe was hot, dense, and remarkably smooth. In some ways, smoothness sounds disordered, but when gravity is included, a smooth early universe actually represents a very special low-entropy condition. Gravity tends to make matter clump into stars, galaxies, and black holes. A universe where matter was spread very evenly was not the most generic gravitational state it could have had. That low-entropy beginning gave the universe room to evolve. Stars could form, heat could flow, structures could grow, records could be created. Memory, fossils, radiation, history, and aging all depend on this deep difference between past and future. Why the early universe had that special low-entropy condition remains one of the deepest unsolved questions in cosmology. We know the arrow of time exists. We know it is tied to entropy. We know the early universe was special, but we do not fully know why. At the smallest scales, time becomes both essential and strangely quiet. Quantum mechanics is the physics of atoms, electrons, photons, and the tiny systems that build the ordinary world. It began from problems that classical physics could not solve. Max Planck introduced the idea of energy coming in discrete packets. Niels Bohr used quantum ideas to explain the structure of atoms. Werner Heisenberg developed the uncertainty principle. Erwin Schrödinger wrote a wave equation for quantum systems. But time occupies an unusual place in this theory. In standard quantum mechanics, position can be represented by an operator, a mathematical tool connected to something measurable. Momentum can be represented by an operator. Energy can be represented by an operator. Time, however, is usually treated differently. It appears as an external parameter, the background variable according to which a quantum system changes. Quantum mechanics often asks how the state of a system evolves as time passes, rather than treating time itself as something to be measured in exactly the same way as position or momentum. This difference matters enormously when physicists try to combine quantum mechanics with general relativity. General relativity treats spacetime as dynamic and curved. Quantum mechanics usually treats time as a fixed background. The two approaches clash. In 1967, John Wheeler and Bryce DeWitt tried to apply quantum principles to the universe as a whole. They wrote an equation, now called the Wheeler-DeWitt equation, that attempts to describe the quantum state of the entire universe. and they found something startling. Time does not appear in the equation. A theory of the entire universe, a theory that should describe everything that has ever happened or ever will happen, does not contain a time variable. This is the problem of time in quantum gravity, and it remains one of the deepest unsolved problems in physics. Some physicists have explored the idea that time could be emergent, that it appears at larger scales from deeper ingredients that have no time built in. Temperature is a useful analogy. A single molecule does not have temperature in the same way a cup of water does. Temperature emerges from the average motion of many particles. It is real, measurable, and important, but it is not a basic property of one isolated particle. Carlo Rovelli, one of the major figures in loop quantum gravity, has argued for approaches in which time is not an external clock standing outside the universe. In loop quantum gravity, spacetime itself is quantized. It is made of discrete, indivisible units. The equations that describe how these units interact are timeless. Time may emerge from the relationships between these fundamental building blocks of space. Rovelli and mathematician Alain Connes proposed the thermal time hypothesis. Time emerges as a statistical effect associated with our incomplete knowledge of the universe. Just as temperature arises from the average kinetic energy of particles, time may arise from our statistical description of fundamental, timeless dynamics. Other approaches also explore the possibility that space-time may be emergent. String theory treats fundamental objects not as point particles, but as tiny extended strings. In some versions, space-time itself may arise from deeper quantum information or relationships. The holographic principle suggests that information describing a volume of space might be encoded on a boundary, but these ideas must be stated carefully. String theory, loop quantum gravity, and holography are serious areas of theoretical research, but none has yet become a confirmed final theory. The experimental evidence needed to settle the question is not yet available. What we can say with confidence is this: time is extremely real in measured physics. Clocks measure it. Relativity shows it changes with motion and gravity. Quantum systems define it with extraordinary precision. Thermodynamics gives it an arrow. Cosmology gives it a history. But whether time is fundamental or whether it emerges from a deeper structure remains one of the great open questions of physics. There is one more dimension to time that we have not yet explored: how your brain perceives it. You do not experience time through a single mechanism. Your brain has multiple systems that track time at different scales and in different ways. At the largest scale, your circadian rhythm, your internal body clock, follows a roughly 24-hour cycle. It is controlled by a tiny cluster of neurons in the hypothalamus called the suprachiasmatic nucleus, which responds to light signals from your eyes. This clock tells you when to feel sleepy, when to feel alert, and when to feel hungry. It is why jet lag feels so disorienting. Your internal clock is set to a different time zone than the one you are physically in. At a shorter scale, your brain tracks intervals of seconds to minutes through a different mechanism. This involves a network of brain regions, including the cerebellum, the basal ganglia, and the prefrontal cortex. The exact mechanism is still debated, but one leading theory suggests that your brain counts pulses from an internal pacemaker, a kind of neural clock that ticks at a variable rate. And that rate is not constant. It changes depending on your neurochemistry, your emotional state, and your attention. Dopamine plays a key role. When dopamine levels are high, when you are excited, engaged, or anticipating a reward, your internal clock speeds up. Time seems to pass more quickly. When dopamine levels are low, when you are bored, depressed, or waiting anxiously. Your internal clock slows down. Time seems to drag. This is why time flies when you are having fun. It is not just a saying, it is a neurochemical reality. Your brain is literally running its internal clock faster when you are engaged. So external time seems to pass more quickly. It also explains why a watched pot never boils. When you are anxiously waiting for something, your internal clock speeds up, but the external clock does not. The mismatch makes time feel agonizingly slow. There is also the oddball effect. If you see a series of identical images, and then one different image appears, the different image seems to last longer, even though it is displayed for the same duration. Your brain allocates more processing resources to novel stimuli, and this increased processing makes the interval feel longer in retrospect. As we age, years tend to feel shorter. One explanation is proportional. A year is a much larger fraction of a 5-year-old's life than of a 50-year-old's life. Another explanation is that novel experiences, which are more common in childhood, create more detailed memories, making time feel richer and longer in retrospect. Routine, by contrast, creates fewer memorable landmarks, and years blur together. Your brain constructs time. It does not passively receive it. The flow of time you experience is a product of your neural processing, your neurochemistry, your attention, and your memory. It is real as any experience can be, but it is also a construction shaped by the particular biology of being human. This connects to a deeper question. The physics of time tells us about clocks, spacetime, and entropy, but the experience of time, the feeling that the present moment is real, that the past is fixed, that the future is open, is a product of consciousness. And consciousness is itself a physical process, running on the same neurons, the same chemistry, the same quantum ingredients as everything else. After all of this, the most honest answer physics can give about time is both firm and humble. Time is real. It is measurable. Clocks record it. Equations use it. Signals depend on it. Causes and effects are ordered through it. Atoms, planets, satellites, particles, stars, and black holes all reveal something about how time behaves. It is not merely a feeling inside the human mind, even though the human experience of time is its own fascinating part of the story. But time is not real in the simple way it once seemed. Newton's absolute time, steady, universal, flowing identically for everyone, was powerful and elegant. It still works beautifully as an approximation for everyday life. If you are making toast, Newtonian time is perfectly sufficient. Modern physics shows that this picture is incomplete. Special relativity says time depends on motion. General relativity says time depends on gravity. These effects are not theoretical abstractions. They are measured. They are used. They are built into the technology that guides aircraft, ships, and the phone in your pocket. The arrow of time is tied to entropy and the low entropy beginning of the universe. Quantum mechanics treats time differently from position and momentum. Quantum gravity suggests that time may not be fundamental, that it may emerge from a deeper structure that has no time built in. We do not yet know which theory of quantum gravity is correct. We do not know what happened at the very earliest moment of the universe. We do not know whether before the Big Bang is even a meaningful phrase. We do not know why the early universe was in such a special low entropy state. We do not know whether time is fundamental or emergent. These are not failures of science. They are frontiers. They are the places where human knowledge reaches the edge of what has been figured out and gazes into the vast unknown beyond. What we do know is extraordinary. We know that time is shaped by speed. We know it is shaped by gravity. We know it is shaped by entropy. We know it is defined by atoms. We know it is experienced by brains. We know it is woven into the structure of causality, separating events that can influence each other from events that cannot. The clock was never simple. It only sounded that way because it was ticking quietly. And the next time you glance at a clock, your phone, your watch, the microwave, remember this: the number it shows is not a universal truth. It is a local measurement shaped by your speed, your height, your gravitational field, and the particular path you are tracing through spacetime. It is real for you, but it is not the same for everyone. Time is not the river we imagined. It is something stranger, deeper, and far more beautiful, and we are still learning what it is.